Perhaps the most common method for analyzing Xanes data is to treat spectrum as linear superpositions of spectra representing individual atomic environments or coordinations. This sort of linear approach is very simple to use, is pretty well justified for Xanes, and is a common approach for other spectroscopies as well, so that in fact a rich set of linear analysis methods and spectroscopic tools can be applied to Xanes. There are some reasons to be a little bit cautious about using these approaches for Xanes, or at least be mindful of how data should be treated in order to keep and to keep an eye out for what can go wrong. Hi, I'm Matt Neuville, and this is part of the video series for using Larch for XAFS analysis. In this video, we'll discuss using linear combination analysis methods for Xanes. In the next video, we'll go a little deeper into what related methods of linear analysis might be used in certain cases. Linear analysis of Xanes is based on the idea that the number of local atomic environments for an absorbing atom is actually fairly limited, and that the different oxidation states or environments, say oxygen and octahedral or tetrahedral coordination, or simple ligands like sulfides, carbonates, phosphates, and so on, are pretty uniform within their class and distinct from one another. Linear combination also relies on the fact that a sample with a mixture of these environments, say octahedral, oxygen, and sulfide, will have a spectrum that is a simple linear mixture of those two basic spectra, and that the atomic environments and spectra won't mix or interact in a more complex way. Together, this all points to the idea that there is not a complete continuum of molecular structures that make up any real spectrum, but a small number of idealized and discrete basis spectra. Again, from a chemical spectroscopic perspective, this turns out to be the case quite often, though maybe not always and maybe not to extremely high precision. Still, spectroscopically, this common observation means that we can ask, what are the chemical species that make up this spectrum, and reasonably expect to get the right answer. It also means that linear combinations of basis spectra for two environments, say again, octahedral oxygen and sulfide, will accurately model a sample that has a mixture of those two environments. From a practical point of view, this makes Xanes analysis very simple and allows a wealth of linear algebra methods developed for other spectroscopies to be used. So to start with, let's read in some iron XAFS spectra, always my favorite example, and we'll see how this works and how well it can work. So I'm going to open some data files that are real Xanes data taken on real samples, and these are meant to be idealized, but they're not perfect data by any means, so they're all good. I think you may have seen these in an earlier video as well. So here we have several spectra. I'm going to just plot them. We have iron in a number of common geochemical environments. We don't need to go into much detail of what they are or how they work, but one of the common things that you might want to say is, can we get a spectrum, an experimental spectrum, and see if it's a linear mixture of these? So let's test that by let's make a combination of spectra with known mixtures and see if we get the right answer. So to do that, I'm going to use the data and the add or subtract spectra dialog. You can use this to try to remove a background from a spectra, but you can also use it in this sense of adding together some spectra. So I'll start with, so let's make a combination of 4 different spectra. I'll say some goethite and some ferrihydrite. Again, if I plot those all together, as some of you may know, the goethite and ferrihydrite are both iron 3+, and so they actually look very similar. So distinguishing these two will be a challenge. But we can also add in some of the other phases as well. So we'll add in a little bit of this and a little bit of that one. I don't know. Sure. That's a pretty distinct phase. Let's add in a little bit of the siderite as well. So with these 4 components, I can just make a linear combination that's, say, C 40% of that plus B of, well, let's just do it this way, A of 10% plus B of, say, 30%, C is 20%, and then D is 40%. So we have a mixture of more siderite, large amount of ferrihydrite, some green rust, and a tiny amount of goethite. We'll just see if we can make that. So if I calculate that spectrum, calculate, and then I can save it. I'll save this as H1 test. And this will be our test spectra, and we'll want to know, here we now have a group here, and we'll want to know if we can make this as a mixture and get the right answer of those components. So to do that, let's go to linear combination fitting tab. We have normalized spectra, and we'll just see if we can get those 4 components. So I'll select those 4 components here. We're going to do a fit in the range between 770 here and 7220. That seems completely reasonable to me. And we're going to use the selected groups as components. So if I click on those, then there's 4 components. The 4 components we know are in our test spectra, and they each have a starting weight of 25%. So then I can select this one group here, H1 test, our test spectra, and say fit this spectra. And this will fit. This will require that the weights for the 4 different components add to 1. It will fit all combinations, so not just the 4, but all combinations of 3, and up to 10 components. So we'll just hit fit, and we'll see how this goes. So here we have a fit here. That looks like it must be pretty close to right. And we also got this panel to come up here. And you can see that now in our results, we have a series of different results listed here with different in order of goodness of fit. Reduced chi-square, there are these other fit statistics as well that should all be the lowest number. They are consistent, so that's good. And we have the best fit here, actually by a good amount, is this fit, which has 30% ferrihydrite, a little less than 10% goethite, about 40% siderite, and 20% green rust. So we got actually the right answer when we said it has those 4 components. How much of each is there? So that's good to know that the math works out well. Down here we have weights, and you can see what the different components are for the different sets. If we look at the second best fit, it's actually not that terrible, but it only has 3 components, 40%, 40%, and 20% of green rust. So this fit is clearly, the right one, but you should be a little cautious because it wouldn't be outlandish to think that with some other amounts of noise or some other artifact in the data that you could get that combination to model this spectrum. And in fact, if we had said, well, I also have some iron foil measurement and Vivianite, and I really don't know what's in that sample, let's build a linear combination that will try to account for all of those. So let's say I don't know which of these 6 is in there or how much. Let's try that fit. So let's do that, where we are adding in things that we know aren't in our sample, and let's see what we get now for our best fit. And here, I want to fit this test one, not the Vivianite. That actually came out to be the right answer if it's all Vivianite. But for H1 test, if I hit that fit group, now here's our data set again. And we get again that it's the same, about the same result, and it threw out most of any other component. In fact, here we see that there are several fits that have with the same chi-square value, and they will have more components, so 5 variables, so 6 components, but it's assigned these other components, the Vivianite and the iron foil, to have 0 weight. And similarly, here this one has an extra component, but it has effectively no weight. So the results are good. Still, they're not perfect. And let's see if we can make this better. Let's go back to the beginning. We picked 4 components that were pretty distinct. But if I go back and plot those data again, you can see that actually these data aren't very well normalized. In fact, I just took the sort of default values. So let's select all of these, and you can see that especially at the high end, the pre-edge looks fine. I'll just leave that alone. But what I would really like to do is to say, let's normalize for such short data range. Let's make sure that we're going all the way out. So 120 volts above the edge in general, but 40 volts is far too close, and there's all these oscillations here. So I'm going to do something that might be a little non-intuitive. I'm going to go further out. Okay, 75, I like that. Let's start at 75, just for a nice round number. But now I'm going to say it's not linear, it's a constant. I'm going to apply that to all of the data sets. And now when I plot those will be much better normalized. So now I can go to the PCA channel, the PCA frame, and do the same thing. Say, to the linear combination panel, run, and say, let's build the components with these models, and then fit our group here. Let's see how that comes out. And now we get a little bit more Gertite and a little bit less Siderite, but we're really getting close to the right values for the starting concentrations that we added. We see the fits are all very good. It rejects any of the other components, knowing that those aren't there. So that's pretty good. But it also tells you that maybe within a few percent, so within say 3 or 5%, that's as good as we're going to be able to do in general for this kind of problem. We can tell the major components at the percent level, things are challenging to do well with this. With these methods. So at this point, I think that covers most of the linear combination. I'll come back to this for another data set. In fact, let's switch gears and go on to another data set. So here I'm going to select all these and remove all of these groups. And let's go on to another example, this one taken from the literature and from the Athena examples. This is data from Maggie Lemke and Bruce Revel from a 2006 environmental science paper, environmental science and technology paper on gold in cyanobacteria. Again, I want to say that I think that this data set is all good, and I'm not trying to change or criticize the results of the paper. In fact, I think everything they did is correct, but we're just going to play with that data set from that paper and look at how you might reproduce those approaches. So I'm going to just take all the data sets. They have some unknowns and some standards here. I'm just going to import them all for these data sets. So here we have a series of unknown spectra, or unknown to us spectra that look like this. If I plot those over this range, there are a lot of similarities between these spectra, but some variations. And so one of the questions you might ask for the unknowns measured here is how many different components are there? How much variability is there? How many different things make up, molecular environments make up these sets of samples? And for that, principal component analysis is exactly designed to answer that question. How many different things, how many different variables are there in a data set? It doesn't tell you well what those are, but it can help you answer how many. I should go back to these data set. Let's go back and check our normalization again, as we found for the iron case. Getting the normalization well here is important. So let's do the same sort of thing. In fact, I'll do exactly the same thing, but also for this data set, I'm going to make sure that I like the pre-edge. For gold or for any L-edge, I'm just going to start this a little bit later. So just make sure that that's right. I'll select all. I'll make sure that that's -50. I think I must have been using another data set, and I'll just copy that to all of the data sets. And then I'll also say, let's go far out here. I don't know what happened there. 350 to 400, and let's make that also constant and copy that to there, copy that to all of the groups, and look at those together. So now those are our normalized data sets. And I think for Xanes analysis, where the data doesn't go up very far, this approach of saying a constant at high energy is a fine way to go. And now when we plot those with our standards, that you can see much more variation among the standards than in the data itself. So probably we will find that these data are fairly consistent with one another and have I'm not super happy with those, and fairly consistent with one another, and appear to be have only a few components. I think I'll start this a little earlier, select all, and normalize those. Maybe that's a little better. It's a little better. I'm happy with that. To say maybe here, and maybe here. So not quite as far out, and a little bit earlier. Let's get that normalization. Let's get that normalization a little nicer. Okay. So to answer the question of how many spectral components are in this data set, we'll go to the principal component analysis, or PCA section, and we'll say we'll build a model. Let's train. This is often called training a model. We're going to build a model with the selected spectra here, the ones that are checked. And this will use an energy range again from 11,870, which is around here, and not very far out. So we'll only look at the immediate Xanes region, maybe 11,850 and 1250, sort of what's plotted there. Let's use those and build the spectrum. And now when we do that, we get a plot here. We get sort of two things that come up. I'll show them one at a time. We get a plot here that shows the components. So if we think about what the components should be for these data sets, obviously we could take the mean of the data, and that's like the major component. The Xanes starts at 0, there's a step. That's the main feature, and the rest of it is sort of decorations on that. So clearly the mean is important. There is the mean. We subtract that off, and then this first component is basically the mean of what's left. That's the next major difference in the spectrum. And again, and then so on, the green curve here, component 2 is the next major spectrum, component 3, component 4. By the time we get to component 4 and 5, there's a legitimate question of, is this just noise? And I might say that, in fact, I would probably call that, there's 3 or 4 components in this data. Maybe there's 4, maybe there's 5. There's probably not 5, there might be 4. So this is what Xanes, or this is what PCA can tell you about Xanes. Model built, 4 of the 8 components have a weight above 0.004. So that looks like we should probably assume that there are, a variation of 4 things amongst these data sets, amongst these different data sets. There are 8 data sets, there's sort of 4 components. That's what our fit is telling us. In addition, we get another plot here, and that is this plot here, which shows a few fit statistics. In here, it shows, the list for each of the components shows the variance and an indication value, an indicator value. In fact, you should be clear that these components here that make up the principal components are not XAFS spectra. They are arrays of data in energy that encode the differences, the variance in the spectra. So again, the first one is the mean. That might look like a real spectra, and you can model as a real spectra, but these are where the spectra vary the most. These energies with these weightings are where the components of the differences. So you could take any of the spectra, add these up in some linear combination, and reproduce the spectra. But you can't say that any of those are actually Xanes spectra. So this plot here for the significant and non-significant components on a log scale is called the Scree plot. A Scree is a the way a mountain falls down. So if I make sure that's on a linear scale, those are the significances, the variations that account for each of the components. As we get to the noisier components, the higher number of components, those variances go down, and we say that's about how the most significant about this level of significance. In addition, there's a statistic called the indicator value, and when that's minimized, that's generally a good way to determine how many components there are. And for this data set, again, I'm going to show that on a log scale the way we normally do. the Scree plot, the significance, and the indicator value both agree that the best result is to say that there are about 4 components in this data set. So that's good to know. And now we can ask ourselves, so if I go back to this data set, plot all of those together, and look at those, and also plot, say, the gold foil. Let's include that. That there in gold, surprisingly, looks like it's all of the data sets kind of have some of that going on in it. I think from a chemical point of view or from a biological point of view, that's sort of known. These cyanide bacteria, gold was added, so it's nanoparticulate gold. So it's expected that there will be some gold in there. So for the PCA point of view, we can ask, now that we have these components, which of these models compounds can be explained by the variance in the data? So which of these model compounds could be explained by the data? So this is often called target transformation, but I'm going to take our components and say, test the current group, gold foil, with this model. And here, this plot will show up. Actually, it also gives some fit statistics here. Chi-square is very low. It scaled the data by a little bit, but here so that's saying with the components made from these unknown spectra, we can reproduce the gold foil, the metal spectra, very well. So almost certainly gold foil metal is in this spectrum. We could ask the same for one of the other standards, the chloride spectra. And there, it's pretty good. It's not quite as good. Chi-square is pretty good, but not perfect. Actually, that's pretty good. There's definitely chloride in there. Wait, test that. And chloride, let's try that with the hydroxide, test the current group. And that looks somewhat worse. Chi-square is 0.4. There's a serious misfit. It does not account for this part of the data. Again, this is showing all the components. The fit is in red to the data, and you can see it had to use a very noisy part of the spectra. There's a significant misfit. I might say that there's probably not much hydroxide in this set of unknown spectra, but we can test the other ones as well. That one also looks like that's not very clear that that's a good model. Sulfide, we could try. I'll just go through these. That one looks pretty good. Again, I'm looking at the red curve and the blue curve. So you might say that like all of these have some more or better ability to fit from those model spectra. So clearly gold foil, probably gold chloride in one of its forms. Actually, now that we're getting to more analysis, I want to select down and plot these two, or plot some of these model spectra together. That shows up in here. And you can see that these are all very different, except that, well, maybe they're not all very different. There's a gold chloride and a gold chloride aqueous, and those are really pretty similar. Whether you can distinguish those two in this analysis, maybe. I think the same is true for these. There's a few here that are sulfide, like. Let me just plot all these, and we can see. I'll just go through this. The gold foil is clearly different. These are different. The hydroxide is really very different from everything else. And then there's a cyanide and a thiocyanide. Those are different. Those are distinct. But then we're sort of getting into the realm of like those are all little kind of blobby and not very distinct phases. So maybe those three separately will show up, and maybe they won't. That might be something that's sort of advanced practice. But what we can do now is, now that we have some idea of what the components are and how many we're expecting, we can go back to our linear combination and say, let's use all of these. Maybe I'll say, for the moment, let's not use the gold chloride or the gold hydroxide. We sort of decided that those weren't necessarily in there, so we'll start with just a few spectra. Let's build a few model compounds. Let's build a model from that, and then take one of our spectra and see if we can reproduce that. Again, it's using this default range, and we're going to do the same thing that we did earlier for the gold, or for the iron spectra. We're going to do this now for the gold, and just look at how well can we reproduce these spectra, the unknown spectra, from what we think is almost certainly has some gold foil and some chloride and so on. And here's the result of that. That's a pretty good fit, just asserting that those are the four components, and there's something like 40%, almost half gold foil. There's a lot of chloride, and there's significant amounts of the other phases too. So we could also go here and just add more of these component spectra. I say use a selected group. So now we have 9 components. Probably not all reasonable to think that they're distinct, and we can take this one data set and fit that. This will take a little bit longer. Since it's doing all of the fits of all the combinations, it scales rather poorly as you add more and more components. We sort of knew that there are only 4 or maybe 5 components, and we told it to try 9. So let's see what we get. I'm not sure what the answer is here. So our best fit, and there's a few, it looks like there's a few that are going to be degenerate in these that really rejected many of the components. So that's interesting. Let's see what got rejected out of this. So here there's a minimal number of components, same chi-square with 4 variables, 5 separate components, foil at metal at 50%, aqueous chloride, and the sulfide and thiocyanide, and some hydroxide at the few percent level. And for that one, that might be the best. That might be the best result. And I'll suspect that, in fact, these other ones with the same chi-square are just repeats of that same result, really, with setting some other component to very low numbers. So so it added some chloride that was aqueous and some that was solid. Those probably add up to be effectively the same number. Okay, so I think that's how you would then approach doing linear combination analysis. You could also then, like, let's look at another one. So as these are all vary a little bit, we can fit this group as well. Try that one. Again, with so many components, it takes a little bit of time to do the processing, but it comes up with a good result. And then you can sort of browse here. So here we have the different sets of data and the results for each one. And here there's only this decided that this, although it's not a perfect fit, again, I think the normalization might be done a little bit better for some of these unknown spectra. We get pretty good results. Plot this fit. And you can, again, as I showed earlier, you can say, let's plot the best 5 fits and see how they vary. Those are all probably identical, really, in their components. You can see chi-square is consistent through all of those. So let's go try another one. Fit this set with those 9 with all the combinations of those 9 components, and you can. Well, I think we'll also see that, as with this result, that that's pretty consistent with this one, whereas this one really had a significant amount of gold foil in that spectrum. So that's linear analysis. I think that that's a good start on what to look for, what to be cautious about, and where you can use linear analysis for understanding the components and what the components of your Xanes spectra are, and how to decide what the best set of components is. If you have any comments or suggestions for how to use PCA or linear combinations for your data sets, leave them in the comments below, or send me a question. And I hope to see you in the next one, where we'll go on and do some more linear analysis on some more interesting spectra as well. So thank you, and see you next time.